In the previous video, we started our discussion of organic PV with exciton generation and the material classification of electron donors and electron acceptor. We'll now continue our discussion with charge separation and how this works in a typical organic solar cell. We have mentioned that doping is not preferred in organic materials, since it will lower the diffusion length of charge carriers even more. By intelligently using intrinsic materials, we can still initiate charge separation of an exciton. Using the concept we discussed, we can theorize that by bringing together an electron donor on the left and an electron acceptor on the right, the interface formed will resemble that of a heterojunction. The lack of doping, however, results in the absence of a depletion layer. The width of the depletion layer is inversely proportional to the doping levels in the materials brought together, which in turn removes any electric field formed by the depletion layer. The heterojunction of intrinsic organic materials therefore lacks any sort of band bending, as can be seen in this figure. When we bring together an electron donor and an electron acceptor, their vacuum levels will align and a misalignment in their HOMO and LUMO levels appears. This produces an electrostatic force at the interface, which can be very useful for the purpose of charge separation. An exciton can be split at this interface if the electrostatic force is high enough. Indirectly, the interface formed will act equivalent to a p-n junction that separates charges. The effective band gap in such a heterojunction interface becomes the difference in the energy levels between the LUMO of the electron acceptor and the HOMO of the electron donor. A typical energy diagram of a heterojunction organic solar cell will look like this. On the left-hand side, we see an electron donor material which is brought into contact with the electron acceptor on the right. The ionization potential of the electron donor is the energy difference between the HOMO and the vacuum level. And the electron affinity of the electron acceptor is the energy difference between the LUMO and the vacuum level. Furthermore, we can see the driving force delta G as the difference in LUMO at the junction. This energy is required to split the exciton by exceeding the electrostatic potential that binds them together. Finally, we can define the open circuit voltage Q, V or C as the band gap of the electron donor minus the driving force. In a normal heterojunction organic solar cell, the organic absorber material has a very high absorption coefficient, which requires an absorber layer with a thickness of about 100 nanometers to maximize the utilization of the solar spectrum. On the other hand, the inherent nature of excitons to recombine easily gives a diffusion length of around 20 nanometers. The total thickness of a solar cell absorber layer is limited by its diffusion length, which in this case is much shorter than what is required for satisfactory absorption of incident light. The probability of absorption of light within a region of 20 nanometers from the heterojunction interface that leads to effective charge carrier separation is very low. This results in a very low quantum efficiency yield, as can be seen in this small animation. In order to reduce the effective path length of these excitons, a so-called bulk heterojunction solar cell is used, in which the electron donor and acceptor material form a sort of blend instead of two distinct, well-defined layers as shown on the left. This reduces the path length of an exciton before reaching a donor-acceptor interface, thereby effectively reducing the probability of recombination and increasing the quantum efficiency of the solar cell. The separated electrons travel through the acceptor layers and are collected at the metal electrode, while the holes move through the donor material and are collected at the front ITO electrode. In the last two videos, we have learned about the concept of excitons and how it is different from charge carriers in semiconductors. We understand how the formation of a heterojunction in organic semiconductors can mimic the working principle of a p-n junction. We have demonstrated how excitons move through these materials and undergo charge separation at the interface. Finally, we discussed the concept of bulk heterojunctions to deal with the very small diffusion lengths in organic materials. We have now covered all the fundamental concepts behind the working mechanisms of organic photovoltaic solar cells. In the remaining videos of this section, we will discuss the various existing commercial organic PV technologies.